So welcome, and we are now moving into the more interesting part of group theory, where we learn about representations and we learn a little bit about how it is applied to real systems like molecules. The applications are actually extensive, molecular physics as well as lattice dynamics, but to lattice dynamics and to condensed matter physics, the application requires knowing condensed matter physics and lattice structures reasonably well. So that would really take us out of the main focus of this course. So we will stay with the basic methods and the basic concepts and the proofs, and then apply primarily to the molecular case, which is a little bit simpler. So to continue from last time, what we are discussing are two things: representation, and within that, character of representation, characters of representations. So these are the two broad concepts we are progressing on now. Last time we had some overview of this, but today we can be a little more formal. So we say that firstly, a representation essentially is a realization of group operations in linear algebra. This is what it really is. What this means is, thus the carrier space is a vector space, vector space V, and and the group elements become matrices D acting on V. The size of V is called the dimension of the representation. So you can, the same group you can represent on vector spaces of different sizes. The size or dimension of V in the usual vector space sense, that is, one way of saying it is the number of basis elements required to represent the vector space, to represent all the vectors. So the dimension of V is called the dimension of the representation. This is a little important. Note, matrices D are size n by n when V is, when dimension of V is n. Okay. So a d-dimensional, n-dimensional representation of a group means that you have n by n. So actually n squared is the size of that linear space, but this is the size of the vector space. Now, in general, one has one can represent same group or realize the same group on vector spaces of different size. So we will get into a bit of terminology. Let us also define some symbols. So symbols to be used are that we already introduced this script D, and the script V is the vector space, and the set of matrices which acts on vector space is called the general linear group. Okay, so let us write this down. Note that matrix algebra has a naturally endowed group structure. Because I mean, even natural numbers have a group structure, because you can add things and subtract things, and so there is some group operation you can identify within your already existing knowledge of this algebra. And here the group structure is that the sum of vectors is a vector and so on, sum of matrices is a matrices. So sum of n by n matrices is a group under addition, but what we will be using is multiplication of n by n matrices which are invertible of determinant not equal to 0. Okay. So these are the two different types. So for example, one is this, but the one we will be using is the second one. Also we have multiplication, and that is what we will be using. So we call this set of in the more abstract sense, in the linear algebra sense, the matrices form a general linear group or the general linear group. Acting on a vector space V, and well, acting on vector space V constitute the group called general linear group, denoted GLV. So there are special cases of this, which we actually in practice we use this notation GL of V. We will be using for a short time, for 1 or 2 lectures, but in practice we denote GLNR be the group of n by n matrices, real matrices. I.e., the vector space is identified to be n-dimensional real vectors. And similarly, we have GL and C. Here all the entries can be complex. All the n by n matrix entries can be complex, and the vector space is likewise complex. It has complex components. So this will be one of our notations that will be required when we are dealing with representations. But GLNR has no restriction. You can have things that will have zero determinants. Then the no, sorry, I'm very sorry, take that back. Because the inverse will not be defined unless, so I think we should add that here. So matrices of the type, I myself get carried away in doing this, all the writing. So we already emphasized that we will be using the second type. So of determinant not equal to 0. From abstract point of view, matrices on acting on a vector space and with determinant not equal to 0. Thank you. Otherwise, it will not constitute a group. So, okay, here it was. So we already said that we want only those that have determinant not equal to 0. So this is called the general linear group. Now we want to move towards, okay, the other notation we use is that in general you can also have we can have n by m matrices where such that a matrices, and we denote them A, such that A maps V into V prime, and clearly by the matrix, so we are switching between the concrete notation of a matrix and a linear operator, but the point is that since it acts on V, it must have as many rows as the size of V. So if dim V equal to, so if it is n, number of rows is n, right, and dim V prime, sorry, V prime equal to m. So just to not get lost, let us draw this. So I have n entries here, this is V. So I must have as many columns. So number of columns must be also n, so that I can multiply this. Then the number of rows, and suppose it produces an m dimensional vector V prime. So the number of rows here n columns. Such a matrix we call m by n, not, okay, m by n matrix. So that's right. So if we have n dimensional V and it gets mapped into an m dimensional V prime, then the matrix must have m rows and n columns. This we will need for a little while. It's not going to be part of major group theory, but in order to prove some important things about representations that have different sizes, we will need this for next 2 lectures. So we also have operators of this type which map V into V prime. Okay. So before we go on, let me just try to, as an interlude, because now we are going to do something a little more technical, where what we want to next prove is Schur's lemma, but we will see an example of where we are going after I state Schur's lemma. So next we shall prove Schur's lemma Actually, it is such an interesting thing that it is a theorem by itself, but you will see later why it is called lemma, because Schur proved it on the way of proving something much bigger. So we shall prove Schur's lemma, which basically says that if there are representations D and D prime such that A times D is equal to D prime times A, okay, such that the size of A matches the required m by n thing. So D is, let us say, m by m, this is n by n. So just picking from here, this means that this is n by n and this is m by m. Then it can take a n by n matrix. If you multiply it by an m by n matrix, then it will convert it into a m by m matrix, and then that can be multiplied on the right by an m by m matrix. Right. So if there is an A such that it kind of commutes with 2 representations or converts one representation into the other, then this A has to be trivial, or it has to be, so either it has to be all 0 or it has to be identity, or D equal to D prime and A is proportional to identity matrix, where n will be the dimension of that D. So using this theorem, which we will prove in a little while, we shall prove what is called the great orthogonality theorem. The great orthogonality theorem, roughly speaking, is row by row and column by column orthogonality among representation matrices. Now a little example, and the example is the very exciting one that we have been considering for a while. This is the S3. Which is, just to remind you again, 2 ways of thinking. It is either all the permutations of 3 objects, but geometrically it is also the symmetry operations of an equilateral triangle, because you get C3 if you just rotate it, but then if you flip it along the 3 altitudes, then you get improper rotations. So if you include those as well, then you get 6 elements, and that is what is S3. And we have been writing out. Okay, so we will. So one way to write these elements is to denote them. The list of elements is, we write out in the usual permutation way, but I think the space will not be enough. Well, let's just write it once. 2, 3, 1. So this is cyclic permutations, and you can see that the cyclic permutations are the usual C3 elements. 1, 2, 3, 2, 3, 1, 3, 1, 2. So it's just rotating the triangle. Now we do an anticyclic permutation. So we say 3, 2, 1. So that becomes anticyclic. And then cyclic permutations of the anticyclic form also work. I hope that's what I have. Yes, 1, 3, 2. Okay. So the first 3 form a proper subgroup, which is just C3. I can write it on the left hand side if there is space. Yeah. Forms just the subgroup C3, and then these involve flips. Now what the next thing we do is write out representations for this. So one thing that I should have talked about in the generalities is faithful versus unfaithful representation, okay, which emerges now. So consider a representation D of size 1. Okay. So actually this is 1 is label, and it's I think at the bottom, or here we write its size n is equal to 1. That is where I represent all elements by 1. So this is the trivial representation which is available for every single group, discrete, continuous, whatever you have. Now this doesn't look like a very exciting representation because it is mapping every operation into 1. Of course, under multiplication, any group multiplication table will be satisfied. So that is a very silly way, but it turns out that like we have 0 in addition, this representation anchors all the irreps. Okay. So the representation is irreducible, though completely unfaithful. It is not homomorphic. It doesn't preserve the, well, it is homomorphic, but it kills the information, detailed information about the group. So such a representation is called unfaithful. So there is another representation also of size 1. So I will write it down because I have to come back to the formal things again. So I will write it down. Just remind me at that point also. Faithful and unfaithful, and reducible and irreducible, we will write out more detail. So the other representation is also one dimensional, is where you put all the proper rotations as +1s and all the improper rotations as -1. So 1, 1, and 1, and -1, -1, and -1. The reason why this works is, you remember that if you do an improper rotation, which amounts to say flip, but if you flip twice, not necessarily about the same altitude, but even some other altitude, if you flip the triangle twice, then it will come back to a form which can be got by simple rotations. So product of any two of these will give you this, and product of these by themselves form a group. So this 1, 1, and 1 is effectively the trivial representation of C3, and the other elements of S3 which are improper rotations get represented by -1, and then they have the correct property. And then finally we have I shouldn't say finally, but because I am telling you the punchline, but the other representation you can think of is the 2 by 2 representations, which are the 3 pi by 2 rotations and the improper ones, the ones that we have been writing with 1 half square root 3 by 2 and those. Here I will run into a space problem, so I will write, so these are the 2 by 2 matrices acting on vectors in xy plane. So let us write those down. So the D3 for the same list again I packed them too closely, but this one is just identity. Then the next one is 1 half times -1 square root 3 minus square root 3 minus 1, and the next one is 1 half, only the signs of square root 3 change, -1 minus square root 3 and square root 3. Then for these we start with one of them gone improper, so that is with first row. Okay, so these are 1 square root 3 square root 3 and -1. So there is a 2 by 2 representation of all these operations like this. Now we define the character of a representation. Actually we should say characters the trace of matrices, I guess one should say traces of the, I will just correct it if you need. The traces of matrices D alpha are called alpha of G, are called the characters of G in the representation alpha. So traces, the traces of the matrices D alpha of G are called the characters of G in the representation alpha. Now the main consequence of this is that the characters of matrices belonging to the same conjugacy class are all the same. Okay. So a result or theorem, are equal. This is because if H1 and H2 belong to same conjugacy class or are conjugate to each other, same thing, then there exists G belonging to G such that G H1 G inverse is equal to H2. But now we, in terms of a representation, this would mean d alpha of G, d of H1, d alpha of H1, d alpha of G inverse has to be equal to d alpha of H2. But we know that the d alpha of G inverse must be represented by the inverse matrix of d alpha. This is because you have to get identity matrix out of this multiplication. So if it is the inverse, this is because d alpha of identity is simply equal to n by n for alpha n dimensional. If the representation alpha is n dimensional, then identity matrix has to be represented by the identity matrix of that size, and therefore the inverse of a particular group element has to be represented by the inverse matrix of that group element. Okay. Therefore, coming back to this, now we take trace of both sides. So therefore, d alpha G, d alpha H1 and d alpha G inverse matrix is equal to d alpha of H2. So if we take trace, has to be equal to the trace of, because under trace you can cyclically rotate the matrices, and so you can bring the d alpha inverse to this side, d alpha inverse d alpha will be equal to identity matrix, so it will become, right, using trace ABC equal to trace of CAB. Everyone knows this? Yes? No? Not sure? If not, I'll write it here. It's a one line proof, because note that this is same as, what is the matrix ABC? It is Aij, Bjk and Ckl. But if I am going to trace it, then I have to set L equal to I, because I have to take trace of this new matrix. So this is nothing but this. But once it is tied up like this, it is equivalent to Cky, Aij, Bjk. So we have suppressed the explicit statement of summation, but we can put it in if we like. So then it's also explicit that there is no commutativity issue. These are just numbers, and there's a big summation over I, j, and k, and so this is just visually to help us to bring C's here, but once brought here, we can think of this as trace of the matrix CAB. Okay. So because of this, trace of ABA inverse just becomes equal to trace of B. Right. Which is what we have used. Therefore, all elements belonging to the same conjugacy class have exactly same character. So thus proved. Okay. But just to as an appendix, we just say that this is the property we have used. So now to go back to our example. So returning to our example, we have these representations. Well, it even fits on the page, right? Good. Yeah. So we see that we can calculate characters of our representation. The characters in this case are trivial. Traces of 1 by 1 matrices are the values themselves. So the trace of everything here is 1. Then the trace, so that at least ensures that everything in the same conjugacy class is the same. Here the trace of the ones connected to identity by usual rotation are all 1, but the trace of the improper rotations are all -1, but at least they are all similar. And remember, the idea of conjugacy was that essentially aside from a change of basis, a conjugacy element does the same thing that another member of the same class does. So these three, which are essentially flips, they either flip around the vertical altitude or the ones that are crossed like this, but they are all flips. So geometrically they have the same operation, and you can rotate one into the other, but just doing that rotation doesn't change its character. In this sense, it is its character, okay, it's like its property. So the character of these three remains the same, and therefore they have the same character -1. The more interesting thing is the characters of these, and we can write, so the letter used for character is chi. So chi2 values here are 2. Then this is equal to -12 and -12, so it is -1. This is -1, and then these, if we see, we will add half and -12, so 0, 0 and 0. So the character of these group elements in the representation which we have called D2, actually we called it D3, isn't it? I'm sorry, this is D3 because 2 is that one with flipped signs, D3. So D3, the character of identity is 2, the character of these two which are proper rotations is -1 and -1. So these two, remember that the identity is always in its own conjugacy class, because G H1 G inverse equal to H2, but if H1 happens to be identity, then G inverse will always give identity. So identity is in its own conjugacy class, so it is by itself. It has its character 2. These two are in the same conjugacy class because they are essentially proper rotations by 120 degrees, and they have the same character. That character turns out to be -1 in this representation, and all these improper guys have the same character, which is 0. Okay. So we can now create a table which is somewhat like a multiplication table, but now only of the characters. We have the class of character, we have 3 character classes. And how do we know this? There is also a theorem, recall, for S3, for Sn, number of conjugacy classes is equal to the number of partitions. Of n. This theorem we proved by writing the notation in terms of cycles. Through cycle notations we check this. So here we have 3 equal to 2 plus 1 equal to 1 plus 1 plus 1. So there are 3 ways of partitioning 3, and therefore there should be 3 independent conjugacy classes, which we also see directly in terms of this list, because they split up like this. So clearly there is this conjugacy class, this and this. So we denote the conjugacy classes by C and then write out their characters. So in the vertical column we write C1, C2 and C3, and so in other words we label the rows by the character class or the conjugacy class, and here we write the character of the corresponding representation. So chi of representation 1, chi in representation 2, chi in representation 3. So just to repeat, what we are doing is, instead of writing the big table, I could write this table, okay, which generates some generic list, some generic way of writing out the elements, and then for each element in 3 different representations I write out their matrix representations full-fledged. In principle I could have gone on, I could have written some D4, some D5, etc., whatever, but I could create a gigantic table or a gigantic list of what is a group element and which matrix it is represented by. But what we find is that from geometric point of view, it's only the character that matters. So instead of listing all the group elements, we only list the conjugacy classes C1, C2 and C3. And instead of listing the entire matrix representation, we simply write the character of that characteristic class in that representation. So here C1 is the, so now we can read back and write down what the characters are. The characters of first 2. So for I call, so by the way, this is the curly C, it's the that represented the cyclic group of size 3. Anyway, unfortunately in books they mix up all the symbols anyway, so it doesn't matter, and from context you know which is which. So I have called here the conjugacy classes C1, C2 and C3. The conjugacy class of 1 is the identity, and for identity we know the character of this and this is just 1 and 1, and the in the representation number 3 the character or the trace was equal to 2. then this remains 1 and 1 boringly, nothing changes. And here for these we see that these two which form the class C2 both have character just 1 and this has character -1. This conjugacy class has character -1, the one of improper rotations. And finally we can write out these happen to have 2, and then because the diagonal elements were cosines of 120 degrees, adding them we got -1. So this is -1 and the character of these is 0. Now we claim that it is not necessary to build any bigger table. For most, at least the molecular physics applications, it's actually sufficient to just know the conjugacy class table and not the big multiplication table or the big matrices themselves. Also, how do you know how many representations you should take? Well, we will prove that there are no more irreducible representations. So these are all the irreducible representations there are for S3, and these are all the conjugacy classes there are for S3. This fact followed from our theorem about partitions, that there are only 3 of these. It also turns out that there are only exactly as many irreps as there are conjugacy classes, which is something to be proved later. Okay, but so this example makes it graphic what we are talking about, and the fact that this is all that you will in general need to understand or split up the vibrations of a molecule and relative intensities of lines and so on.